Good morning. Let us see today cubic closed packing, hexagonal closed packing. What are called cubic closed packing, hexagonal closed packing crystal structures. Although they are closely packed crystal structures, they have voids, they have holes, they have also cavities in the crystal lattice. They are called, there are two types of holes or cavities in the closed packed structure: tetrahedral voids or tetrahedral holes, octahedral holes. Based on these, the structures of crystalline solids are described. Remember, we need to understand what is CCP, what is HCP, and what are tetrahedral, octahedral holes. In order to understand, in order to write the structures of crystalline solids like rock salt, fluorite, antifluorite, zinc blende, woodsite, normal and inverse spinel, we need to know what are CCP, HCP and their cavities and holes. There are two types of closed packed crystal structure. One, cubic closed packed crystal structure. Another is hexagonal closed packed crystal structure. In the case of cubic closed packing, it is also same as face-centered cubic unit cell. It is of ABC, ABC, ABC type, whereas hexagonal closed packed structure is AB, AB, AB type. Okay, now let us see how the atoms are arranged in cubic closed packed structure, crystal structure. Here in A, there are the atoms are arranged in hexagonal manner. In B, the atoms are arranged in triangular manner, and in C, the atoms are arranged again in triangular manner but inverted. This is inverted. You see, this is here, and this is this side facing U. So A, B, C, and this is ABC are repeated in 3 dimension. Therefore, it is called ABC, ABC type, and also cubic closed packed structure. In hexagonal closed packed structure, there are 6 atoms arranged in hexagonal manner and 3 atoms are arranged in triangular manner. They are placed over one over the other, and this is of again AB, AB, AB type. Okay, this is the structure of hexagonal closed packed structure. Although they are closely packed, they have same packing efficiency. We have calculated the packing fraction in our previous solid state lesson. Please watch that. There are two types of we say they are closely packed, but there are cavities. Still, there are cavities in the crystal lattice. Okay, there are two types of cavities, voids or holes in cubic or hexagonal closed packed structure. They are called tetrahedral holes, octahedral holes. How the tetrahedral holes are formed? I have shown here how the tetrahedral, octahedral holes are produced or generated. Now, let us consider the 3 atoms are arranged in triangular manner. Now you see there is a cavity. This is the cavity in the crystal lattice. And when you place another atom over it, okay, you will get the tetrahedral cavity or tetrahedral hole. This atom is surrounded by, is coordinated by 4 atoms. So the coordination number is 4. Okay, let us see how the octahedral hole is created. There are 3 atoms arranged in triangular manner, and another set of 3 atoms are arranged in triangular manner and are inverted, and there is a hole here. This is called octahedral hole or octahedral void or octahedral cavity, and this atom at this is surrounded by 6 other atoms or coordinated by 6 other atoms. So the coordination number of octahedral hole is 6. Okay, you see the size of the atoms will be small so that it will fit in the tetrahedral hole, the sizes are very small here, and this is size is little bit bigger. So only small sized atoms can only fit the cavities. How are tetrahedral holes are located? Where are tetrahedral holes? In cubic, for example, in face-centered cubic lattice or in cubic closed packed structure, crystal structure, where are the tetrahedral voids? I have shown here there are 8 tetrahedral voids. For example, in FCC, this is the FCC arrangement. Okay, there are 8 cubes, 1, 2, 3, 4, 5, 6, 7, 8. Therefore, there are 8 small cubes. Each cube has one tetrahedral hole at the center of the cube. This is the tetrahedral hole. This atom at the tetrahedral hole is surrounded by 4 other atoms. Okay, this and opposite. Therefore, there are 8 tetrahedral holes per CCP. Okay, and in FCC there are 4 atoms at the corners and face centers. Therefore, there are 4 atoms in the FCC. Now, there are 8 atoms in the tetrahedral holes. Therefore, for each atom in the FCC, there are 2 tetrahedral holes. Okay, this is commonly asked. Here, where are the octahedral holes? This is the cubic closed packing or FCC unit cell structure. Octahedral hole is present at the body center. You see, this is surrounded by 1, 2, 3, 4, 5, 6. Okay, there are the coordination number is 6. This is one of the octahedral hole at the body center. Similarly, there are 3 other octahedral holes at the edge centers. This is edge center. This is edge center. How many edge centers are there? There are 12 edge centers. There are 12 edge centers. Okay, if you count, you take a cube and count the number of edges. There are 12 edges. Now these 12, each edge is shared by 1, 2, 3, 4. Okay, therefore each edge center contributes 12 into 1 by 8. Therefore, there are 4 octahedral holes in FCC structure or CCP arrangement. Okay, here I have shown, for example, there are 4 atoms in the FCC arrangement and there are 4 octahedral holes. Therefore, for each atom there is 1 octahedral hole. This is asked in competitive exams, remember. Using the CCP, HCP arrangement and octahedral holes and tetrahedral holes, the structures of various inorganic compounds are obtained or described. How the rock structure, for example, the first one is rock salt, example NaCl, KCl, NGO, SRO, CaO, etc. In this case, Cl minus anions form FCC unit cell. That is, Cl minus occupy the corners and at the face centers. Okay, therefore there are 4 anions. And cations occupy all the octahedral holes in rock salt, remember. So we need to know octahedral holes and also CCP arrangement. Cations occupy all the octahedral holes. Therefore, there are 4 octahedral holes. Therefore, A4, B4. On taking ratio, you will get AB. This is the formula of rock salt. Let us see the fluorite crystal structure. In fluorite, for example, calcium fluoride, uranium dioxide, thorium dioxide. In this case, in rock salt, anions form the CCP, whereas in fluorite, cations form the CCP, FCC unit cell structure. and therefore there are 4 Ca2 plus ion, and anions here, the you see uranium is very big, thorium is also very big. Oxide compared to uranium, thorium, oxides are very small. Very small sized ions occupy the holes. I have already mentioned you. Therefore, O2, remember O2 occupy the anions, occupy all the tetrahedral holes. Therefore, all the tetrahedral, 8 tetrahedral holes are occupied by the oxide. So the formula is A4B8. On taking ratio, the formula is AB2. So this is of AB2 type. This is of AB2 type. Let us see now antifluorite. It is just opposite. It is just opposite, interchange. Anions, cations here. Now you just interchange this. Okay. Now anions form the cations form the FCC. Here anions opposite, just opposite. Okay, that's all. And also this is CaF2, this is Li2O. These two interchange the position. Li2O, Na2O, K2O, Rb2O, etc. So same as before, anions form the FCC unit cell structure. Therefore, there are 4 oxide ions. Cations occupy all the tetrahedral holes. Therefore, 8, and also 2. This is 1:2. Therefore, Li should occupy all the tetrahedral holes. So the formula is Li8O4. That is the ratio. After ratio, it is A2B type. This is of A2B of type. Here I have shown the differences between fluorite and antifluorite. The same we have already discussed. This is A is divalent, B is monovalent. Here A is monovalent, B is divalent, just opposite. The arrangements are also opposite, but same. They have the similar. Let us see the third important structure. This is again AB type, zinc blend. It is of cubic closed pack structure, FCC structure. Example, zinc sulfide BuO. There is another zinc sulfide, woodside. It is of it is called woodside. It has hexagonal closed packing structure, whereas this is hexagonal closed packed structure. In zinc blend, anions, zinc blend, anions are large size. Anions are large size, therefore they form the CCP FCC unit cell. Therefore there are 4 sulfide ions, and cations, because this is 1:1. All the cations occupy the tetrahedral holes, or half of the tetrahedral holes. One is here, then another is here. One is here, then opposite. It will be of opposite. Therefore, cations occupy half of the tetrahedral holes. The formula is Zn4S4, Zns. Another important type is spinel. There are 2 types of spinel crystal structures: normal spinel and inverse spinel. What are normal spinel and inverse spinel? We will see example: ZnAl2O4, MgAl2O4, ZnFe2O4, and Fe3O4 magnetic oxide, nickel Fe2O4. In this spinel, remember, in both the cases, the first one is divalent. This is A is divalent and B is trivalent. A is always divalent, B is always trivalent. Remember that. Okay. And oxides, here you see 4. Therefore, oxides form CCP, FCC. Therefore, there are 4 anions. Okay. Similarly, here also. Now, this A divalent ion occupies one of the tetrahedral hole in FCC, because only one is present, AB type. Therefore, A is occupying one of the tetrahedral hole in FCC. For example, zinc 2 plus divalent. And these 2 trivalent, 2B trivalent cations are present in two octahedral holes of FCC. For example, Al3 plus, Fe3 plus, trivalent. But here you see one will come. This is B. This is B is trivalent. Here also B is trivalent. A is divalent. B, one of the B occupies tetrahedral hole, not A. See, that is why it is called inverse. B, one of the B, trivalent, here divalent, okay, trivalent occupies tetrahedral hole in FCC structure. For example, Fe3 plus, okay, and therefore this goes inside. This goes inside. Therefore, this AB, A1A and 1B occupy two octahedral holes. They are present in octahedral holes. Therefore, the formula here is A, B, 2, B2, B, O4. Similarly, here also AB2, O4 only. This is B and AB and O4. Okay. Now we will see what is the reason why Fe3O4 forms inverse spinel, why Mn3O4 forms normal spinel. These are often asked in GATE, CSIR, even in JAM, NEET, etc. If trivalent in octahedral hole, crystal field stabilization is greater than A2 plus, then normal spinal structure is obtained, is observed. For example, it will be easily understood. Mn3O4, Mn2 plus, Mn3 plus twice O4. In Mn2 plus D5 electronic configuration, that is, we have already seen in crystal field stabilization energy calculation, it is equal to 0. Therefore, so it is present in the, if the crystal field stabilization is 0 or less, then it is present in tetrahedral hole. It prefers to occupy the tetrahedral hole. Therefore, you see Mn3 plus is D6, the crystal field stabilization is greater. So, this is Mn3 plus, the crystal field stabilization energy is greater. Therefore, B, the trivalent ions are present in octahedral holes. Okay. So, Mn3O4 is of normal spinal, crystal structure. In MgAl2O4, for example, both are not transition metal ions. So the crystal field stabilization energies are 0 for both. So they are of normal spinal structure. There is no preference for tetrahedral or octahedral. Whereas in the case of magnetic oxide Fe3O4, Fe3 plus D5, crystal field stabilization is equal to 0. You see now Fe2 plus D6. So the crystal field stabilization is greater than, now this is opposite. Therefore, this is our inverse spinal structure. Therefore, Fe2 plus is present in the, not in the crystal field stabilization is greater. Therefore, it prefers to occupy octahedral hole, octahedral unit. Similarly, in NiFe2O4, Ni2 plus D6, okay, crystal field stabilization is greater. Therefore, it occupies the not the tetrahedral hole, because divalent is not in tetrahedral, octahedral hole. Therefore, this is also of inverse spinal crystal structure. Okay, so these are very, very important, often asked in GATE, CSIR, etc. Please study well. Thank you for watching.